On slide 19, we show the output that we see when we run this little program. A circle is drawn, and then a scaled circle is drawn, then a square is drawn, and a scaled square is drawn, and finally a polygon is drawn, and a scaled polygon is drawn, and at that point the program is over. But we have a puzzle here, because the destructors for circle, square, and polygon should be displaying these little messages, tilde C for circle, tilde S for square, tilde P for polygon, and we're not seeing those. So we have a problem here. Let's think about this. Now, in the base class, in shape, we declared draw as a virtual function. We declared scale as a virtual function. We declared rotate as a virtual function, so that if we have a base class pointer pointing at a derived class object, the correct derived class draw or scale or rotate function is looked up at runtime. But here, when we say delete SV sub I, which we should have SV sub I here instead of star IT, that will delete the memory that was allocated with new and invoke the destructor for the class. But we didn't specify any destructor for the shape class at all, and we certainly didn't specify the destructor for the shape class as virtual, which would cause the correct derived class destructor to be called. So we need to fix that flaw, and we show that on slide 20. If you have an abstract class, you have to specify a destructor for that class, and the destructor has to be virtual. So here we've added to our shape class a destructor for the shape class, and we specified that it is virtual. So now, when we have a pointer to a shape, and we do a delete on that pointer, not only will that deallocate the space that the pointer is pointing to, but it will also invoke the correct derived class destructor that shape pointer is actually pointing to. So if we have a shape pointer pointing at a circle, and we say delete the pointer, that will invoke the circle destructor. If we have a shape pointer pointing to a square, and we say delete the pointer, that will invoke the square destructor, and so forth. So this is the only correction that we need to make in our class hierarchy, and when we compile and re-execute the program now, we will see a circle drawn on the screen. Then the circle will be scaled by a factor of 2, and we'll see that circle drawn on the screen. Then we have the delete of that pointer. So notice that we see the derived class destructor called first, and we see tilde C indicating that the circle destructor has been invoked. And then the base class destructor is also called. So we see the tilde shape message. Remember, we said that when you call constructors for objects, that the destructors for those objects are called in the opposite order. The same thing is going on here. When we create a circle, that first invokes the constructor for the underlying class shape, and then invokes the body of code that remains for the circle class. All right, so the inner shape is constructed first, even though in this case the shape class doesn't actually have any constructors. The inner shape is constructed first, and then the outer circle, the higher level circle, is finished being constructed. So when we delete a circle, that is, we delete on a pointer to shape that's pointing to a circle, that's going to call the destructor for the circle class first, and then the destructor for the base class shape next. Okay, so we've drawn a circle, we've scaled the circle and drawn it again, we've deleted that pointer, which causes the derived class destructor to be called first, and then the base class destructor to be called. And now in the second iteration through the loop, we draw a square, we draw a scaled square, and then we delete that pointer. All right, so now we have a pointer to shape that's actually pointing at a square. So that's going to invoke the square class destructor first, followed by the shape destructor, the base class destructor. And similarly then for the polygon. The polygon is drawn, the polygon is scaled by 2 and drawn again, and then we delete the polygon, which invokes the polygon destructor, and then the base class shape destructor. The circle class destructor doesn't actually do anything other than display a message. Likewise, the shape base class destructor doesn't do anything other than displaying a message. And the square destructor, although we didn't implement it, doesn't do anything but display a message. However, for the polygon destructor, remember that we looked at that back on slide 14. The polygon destructor is doing something very important because we allocated these two int arrays with the addresses of the first elements of those stored in the members XA and YA. So we had better have our destructor delete the array XA and delete the array YA, or we will have created a memory leak problem for ourselves. It's a very common bug, and it's something that I continue to do, I'm embarrassed to say, to forget to declare your base class destructor as a virtual function. And this often leads to memory leak kinds of problems. Here on slide 22, we're showing a reminder of our employee, manager, CEO class hierarchy with constructors for each one of those. Remember that an employee has an ID number, a name, and a rate, and so the constructor for the employee class initializes those private data members. The manager constructor also needs to be given an ID number, a name, and a rate as arguments, as well as a job title and a budget. The manager constructor simply passes down to the employee constructor the initial values for the ID, name, and rate. So there we see that when we construct a manager, the first thing that happens is that an employee is constructed, and then we complete the initialization of the manager. So in essence, when we construct a manager, we're constructing an employee first, and then finishing constructing the manager. And continuing on with the CEO, when we construct a CEO is a manager with the addition of a profit target and a bonus percentage. So the constructor for the CEO class first constructs the manager, which first constructs the employee and then completes constructing the manager. And when the manager part inside of the CEO is finished being constructed, then we complete constructing the CEO by initializing the profit target and the bonus percentage. Okay, so when we invoke the CEO constructor, that first builds the inner employee part, and then completes building the inner manager part, and then completes building the CEO part. So you want to think of this as being sort of like Russian dolls here. When you construct one of these, you start with the innermost doll and you add the shells for the outer dolls. That's construction. And when you destruct from the outside in. That is, you disassemble the nested dolls starting from the outside and working your way in. This is the same idea as far as the hierarchy of how constructors and destructors are called. We said, by the way, that when you create an abstract class, you must specify that the abstract class's destructor is virtual. Actually, that applies here to the employee class as well, because in this case, for our employee, manager, CEO hierarchy, the employee class is the basemost class, and if we need to have destructors for employees, managers, and CEOs, and we need to be able to allocate and deallocate these things on the heap on the fly, the employee class's destructor had better be virtual, so that when we dynamically allocate a CEO and later deallocate the CEO, the destructor for the CEO will be called first, followed by the destructor for the inner manager part, followed by the destructor for the inner employee. It's reasonable to ask, well, why aren't destructors virtual all the time? And the reason is that using virtual functions, which implies setting up this vtable in memory and having to indirect on functions through that vtable, takes a little more time than just having functions that are hardwired. And one of Stroup's design principles for the C++ language was that you never have to pay an efficiency cost for any feature that you don't plan to use. So if you want to use virtualness, you have to ask for it. If you don't ask for it, you don't get it. All right, so let's use what we've learned about class hierarchies, abstract classes, virtual functions, and virtual destructors by taking a look at the creation and evaluation of arithmetic expressions. Now here, thanks to the PowerPoint Apply to All facility for the footers, I've got my name as the copyright holder of all of this stuff, but in fact I stole this from Professor Stephen Rarig, so his name really should be there. My apologies to Steve. So an arithmetic expression consists of a collection of terms. Term is an abstract idea. Some of those terms are constants, like 5 or 17. A constant is a kind of term. Some of the terms are binary operators, like plus, minus, times, divide. Binary operator is also an abstract class. It is a kind of term, and then we have specific binary operators. Plus is a kind of binary operator. Minus is a kind of binary op. Divides is a kind of binary op, and so on. Here on slide 25, we have a diagram of this class hierarchy. Term is the base class of everything. Kinds of terms include expressions, variables, and constants. Okay, so we've talked about a constant like 5 or 19 as being a kind of term. A variable, which you will deal with in the homework, is also a kind of term. And also, an expression is a kind of term. Now, an expression is composed of a sequence of terms hooked together by binary operators like plus or minus, or perhaps preceded with a unary operator like plus or minus. So in the diagram with these blue-green circles on the right, we have an expression tree representing the arithmetic expression 1.1 plus 2.2, that quantity plus 3.3. We want our code to be able to store these expressions and to be able to display the expressions in a human-readable form, and also to be able to compute the value of an expression. So let's take a look at the code for this, starting on slide 26. All right, we include headers that we're going to use. One of these headers, which is new here, is the S-stream header. Previously, we've used the F-stream header, which allows us to either read from or write to files on disk. So if you create an OF stream object, that's an output file that you can insert text into using the insert or put to operators. Whereas if you create an IF stream object, that creates an input file that you can extract or use getLine to read information from an input file. S-stream here is going to enable us to insert characters into a string object or to read characters from a string object. That is, we can treat a stirstream object as though it were an output file or an input file. Okay, so our basemost class is term. And term is very simple. Term has a constructor that doesn't do anything. It also has a virtual destructor that doesn't do anything, but it's very important for that virtual destructor to exist, since we're using term as an abstract base class for all of the various specific kinds of things that are going to make up our expressions. The two functions that we're going to need to have overridden at each higher level in this class hierarchy are called toString, which is going to take the current term and convert it to a human readable string, and toValue, which is going to take the current term and produce a double value of that term. Now, term itself, of course, is abstract, so we're establishing toString and toValue as pure virtual functions in the term base class. Now let's look at constant. On slide 27, a constant is a kind of term. It has a private data member called value containing a double, and notice that its constructor simply assigns the argument value provided to that value data member. The destructor is virtual, and the destructor does nothing. Now, since we've declared the base class destructor to be virtual, it's actually optional to declare this derived class destructor as virtual, but it's fine. And since we're not allocating or deallocating any memory here, it's not necessary for this destructor to actually do anything. Next we have the toString and toValue member functions for this concrete class. Constant is a concrete class. We can actually have constants, whereas term is an abstract class. We can't actually have term objects in our code directly. We can't say term t in our main function, but we can say constant c parentheses 7 to create a constant object named c containing a 7. Okay, so toString and toValue have to actually do something in the case of a constant. Let's look at toValue first. toValue is very simple because all it needs to do is to return the value of the value private data member. toString is a little bit messier. We're creating an OStringStream object named OSS. That data type is described in the SStream header that we showed over near the top of slide 26 over here. And what's nice about the OStringStream class is that we can treat it like a file, and we can simply insert the value of this data member named value into OSS. And then to obtain a string object from OSS, we can use the member function stir. Okay? So we create an empty OStringStream object named OSS. We insert value into OSS, which will take that double value and convert it into a sequence of characters. And we can then obtain that sequence of characters as a string object by saying OSS.stir. And we are returning that string as the value of this function. Okay, so that's all we need for the constant class. Now let's look at the BinaryOp class on slide 28. And on the right-hand side, I've redisplayed slide 25, which shows the hierarchy of these classes. We're going to simplify the hierarchy slightly and just leave out expression and move up BinaryOp to the same level as constant. Okay, so on slide 28, here we have BinaryOp is a kind of term. Now, a BinaryOp requires two terms to be combined together, either added or subtracted or divided or what have you. And what we're going to receive as arguments into the BinaryOp constructor is a pointer to the left-hand term and a pointer to the right-hand term. And we're going to store those values into these left and right private data members, which are pointers to term. Now, we could have used member initializer list notation to initialize left to LF and right to RT, but our screen is a little cramped, so we've written it out vertically here. Then we also have a virtual destructor for BinaryOp that deletes the left and right terms. Those are the only member functions that BinaryOp provides, namely a constructor and a destructor. We've declared the destructor virtual, although technically we wouldn't have needed to do that since the term base class destructor is already virtual. Now, I want to point out here that BinaryOp is still abstract because we did not provide any overrides for toString and toValue. Okay, so since we did not provide specific overrides for toString and toValue in BinaryOp, BinaryOp is still abstract, the same as term. Another thing that we've done here, since this is an abstract class to make our lives slightly easier, is we've gone ahead and declared the data protected. As a general thing, protected data is bad, but for an abstract class where you can't really use the class unless you inherit from it anyway, using protected data is okay. All right, next up we have plus, which is one of the possible binary operators that we might define. Okay, so plus is a kind of binary op. It is a concrete class, not an abstract class. It has a constructor that receives pointers to the left and right term on either side of the plus symbol, and plus simply passes those down to the BinaryOp base class constructor using the member initializer list. Plus has a destructor that doesn't need to do anything, and here we have got toString and toValue defined. Now, what the toString function does is to compose a sequence of characters that is easy for a human being to read. That is, if we ask to see a representation as a string of this plus binary operator being used, then what we're going to see is an open parenthesis character followed by the string representation of the left-hand operand, followed by a plus symbol, and then a human readable representation of the right-hand operand, and finally a closing parenthesis. So we would see something like open paren 3.3 plus 2.2 close paren if we ask to see a plus object displayed as a string. ToValue is similarly straightforward. The value of a binary plus on two double operands is simply the left-hand value plus the right-hand value. All right, so we would do the same kind of thing for minus, times, divide, and here finally, on slide 30, we have an application exercising these various data types. In fact, let me redisplay slide 25 again, because what slide 30 is doing is building this tree that's shown in these blue-green circles. All right, so the first thing we do is to create a new constant containing a value of 1.1, and the variable c1 is pointing to that new constant. Then we create a constant 2.2 that c2 is pointing to, and a constant 3.3 that c3 is pointing to. So at this point, if we look at our diagram, all we would have is 1.1 with c1 pointing at it, 2.2 with c2 pointing at it, and 3.3 with c3 pointing at it. But now we create a plus binary op, and plus has as its two children c1 and c2. So that is this binary op here, this plus symbol, and its left child is the constant that c1 is pointing to, that is 1.1, and its right child is the constant that c2 is pointing to, that is 2.2. Then in the fifth statement here, we're creating plus with the plus node, P1, as the left-hand side, and the constant, C3, as the right-hand side. So now we have created this topmost plus object. P2 is pointing at that topmost plus object. P2's left child is P1, and right child is C3. So we have now constructed this tree representing this expression. When we invoke toString on the object that P2 points to, well, recall what happens. toString is going to display a parenthesis and then the left-hand side with toString called on it, and then a plus symbol, and then the right-hand side. Now, the left-hand side here is a plus. So we're going to end up recursively calling toString again to handle this lower level plus P1. And so in that recursive call, what we'll get all right, my highlighter highlighted the leftmost parenthesis, which I didn't want. But that inner recursive toString is going to produce this string containing open paren 1.1 plus 2.2 close paren. That string is then going to become this left-hand side of the top level plus toString call. So that becomes the left-hand side with an open parenthesis in front of it, and then a plus and a 3.3 and a close paren. So there is our toString part. Here we're displaying an equal sign, which simply comes out as an equal sign, and then we're using the toValue function of the BinaryOp that P2 is pointing to. And toValue, remember, is taking the left-hand toValue and adding it, this is literally an addition operation, to the value of the right-hand side. Now, in the initial call of toValue, the left-hand side is itself a plus. So we call toValue recursively to compute 1.1 plus 2.2, which gives me back a 3.3, and then we add that 3.3 to the right-hand side in the top level, and we get ourselves a 6.6 as our result. Okay, and that's it. So we now have a relatively straightforward expression evaluator, assuming that our expression only consists of constants and plus binary ops. We can add, minus, times, divide, and so forth.